Oh,
okay, perfect.
Okay, so it's my pleasure to introduce Petr Glivický, who actually was with us here a few years ago. Was it 3 years ago for a semester at CUNY, and now is speaking from Salzburg. And he will be talking to us about omega-iterated non-standard extensions of N and Ramsey combinatorics. Welcome, Petr.
Thank you, Roman. Yeah, actually, I need to correct you. It was 5 years ago already.
Oh, time flies. Oh, it looks.
Time flies. Yeah.
It seems like yesterday. Okay.
Okay, so thank you again for having me here. And today I will be speaking about non-standard combinatorics or non-standard theory of Ramsey combinatorics, and most of all about the structure of the omega-iterated non-standard extension of the natural numbers. So I start just very simple for everybody, even if you don't know much about non-standard methods or non-standard analysis. I will go very quickly through, but I will say most of the important stuff. So the scheme or the framework for the non-standard methods that I will be using is basically the following. Classically in mathematics, we have the universal class V of all sets. That's classical mathematics. And in non-standard methods, in the framework which I will be using, this will be the picture or the scheme that contains everything important. Besides the universal class V, we also have two other classes, S and I, called standard and internal universes. And there are some relations between them. So I will get to the details on the next slide, but there's some isomorphism, some elementary subclass, transitivity property, and something about saturation and almost universality. I'll get to the details just in a few seconds. Okay, I forgot to say that whenever you want to ask me, then just ask the question. I will be glad to interrupt and answer. Okay, so this is again the same picture as on the top of this slide. And the main idea why we are using this picture is basically that in the classical world of mathematics, in the V, in the universal class of all sets, we don't have in classical mathematics such things like infinitesimals in real numbers or infinitely large natural numbers. And we would like to add them somehow. Of course, we cannot add anything to V because V already contains everything. So we do the trick. We create an isomorphic copy of the universal class, call it S. So there is some isomorphism which creates a copy. That's very important mapping called star, which I will be using all the time during this talk. And then we extend this copy, this S, which is called standard universe, is extended. It can be now extended because it's smaller than V to a larger universe, which is denoted I, called internal universe, because it's somewhere in between S and V. And this I is exactly the thing where all the new ideal or non-standard elements are. So the infinitesimal real numbers are in this I, the infinite natural numbers are there, and much, much more than that. So that's the basic idea and terminology. If you want to have some more specific idea how this is done, then you can very easily, as logicians, you can very easily imagine, because the construction of this picture of these three classes actually is the ultra power construction. So the internal universe is exactly equal to a very specific ultra power of the universal class with a certainly and carefully chosen ultrafilter so that all the properties which we require are maintained. And the standard universe is a subclass of this ultra power which consists of the equivalence classes of constant functions. So you can think about it in this way if you want, but we will not need the internal structure of S and I as the ultra power and the constant functions. We will talk about all the non-standard stuff only using this as the topmost level, we will not go deeper. We will not need to go deeper. But if it helps you, you can always imagine the ultra-power construction below. And in this construction, the important mapping star, of course, is the mapping that takes every element, every set from the universal class to the equivalence class of the constant function, which is constantly equal to x. Okay, so that's the main idea of the three universes of the non-standard methods. And here are some specifications or details to all the things which are written in the picture. So what is isomorphism is should be clear. I just note that it's isomorphism with respect to all the epsilon formula, so with respect to the language of set theory. Also, what elementary substructure or subclass means should be clear to all logicians, so it's written here just to be complete. The transitivity property between I and V. I is a transitive subclass of V, which means that it's close under elements of elements. So any element of I is actually already element of I, which is not perhaps that known as a term, is what almost universal means. So I is required to be almost universal, which means that any subset of I is actually subset of some element of I already. So the elements really cover the class almost completely. And the last thing, again, shouldn't be problematic. The kappa saturation. Kappa is a cardinal, which is only required to be uncountable. And that's a parameter of the construction which we can choose arbitrarily. Usually uncountable is enough in some other parts, and we will use it today as well. We require that it's larger than the continuum, but other than that, there are almost no requirements on the size of this cardinal number kappa. And kappa saturated means exactly what you would expect. Any centered system of elements of I of size less than kappa has non-empty intersection. So these are explanations of all the words that appear in the basic scheme of non-standard universes. And we can very quickly move to some basic fundamental principles of non-standard methods that some of them I will be using during the talk. So probably the most important one is the so-called transfer principle, which is a very simple thing. It says that for delta 1 formula, so whenever phi is delta 1 formula of set theory, in the language of set theory, then we can arbitrarily add stars to the parameters of the formula, to the variables, and the truth of the formula doesn't change. So for any x's, phi x is equivalent to phi star of x, but only for the delta 1 formulas. For more complex formulas, this doesn't hold anymore. And this, yeah? Somebody want to ask something? Ah, sorry, I heard somebody. Okay, so now the consequences of this include absoluteness or star absoluteness of delta 1 definable relations and operations. So whenever a relation or an operation is definable by a delta 1 formula, then it's also absolute with respect to the mapping star. So in this sense, Rx equivalent to R star of X, or for the operation star of the operation is operation on the start arguments for delta 1 definable, which is most of the basic set theoretic relations and operations. Actually, also the delta 1 comprehension is star absolute, which means that whenever we define a new set using a comprehension with a delta 1 formula, like on the left side of the equation down, and we star the resulting set, then it actually is the same thing as starring all the parameters inside and defining the set by comprehension from the start U with the start parameters Z. So we can factor in and out the mapping star from the comprehension definition. Okay, so those are some basic principles which I will be using. Another that are also quite important are some principles which concern the set of standard elements. So the S is the standard universe, the set of all the standard elements, which are exactly the star images of sets. So S consists exactly of all the star X, where X is any set. And the first thing which is quite good to know is that when we have the star of X, and we want to look what standard elements are inside of this set, then the standard elements in star of X are exactly the stars of the original elements of the set X. And I very rarely, but at one or two places for brevity, I'm using the shorthand for the intersection of any of the star of X with the standard universe, which is denoted by sigma S. It's the standard part of the set X. Okay, so certain complement or reversed thing about the standard part is the so-called standardization principle, which says that not only every standard part of any set is just the set of the standard elements which are in the original, but also any set of standard elements, any set of elements like star U, where U is in X, any set of standard elements is of this form. So any set of standard elements is actually the standard part of some set. And the last of the three propositions on this slide is the one which says how starring of finite and infinite sets work. So actually you have the two cases. When X is a finite set, then the start of the finite set is exactly equal to its standard part, basically exactly equal to the set of the stars of the original elements. But when the X is infinite, when the set X is infinite, this is no longer true. And for the infinite set, the star of infinite set actually contains always more than just the stars of the original elements. They are always there, but for infinite set, another elements are present, and the elements, the new elements in star of X, which are not stars of the original ones, are so-called non-standard elements of the star of X. They don't belong to the standard universe. And actually, there is always at least kappa, many of them, where the kappa is the cardinal from the framework of non-standard methods, which is used in the saturation property. Actually, this is exactly how you would prove this thing. You would use the saturation to say that there must be at least kappa of elements different from these. I will not do the proof, but it's very easy. Okay, so finally getting to something more interesting. And that's something which will be very important for today's talk, because we will be talking about iterating the mapping star. So not only using star once on some set, but using it twice, 3 times, and actually any finite number of times. So for this purpose, we define the mappings n star for any natural number n by induction. So 0 stars is nothing, that's identity. And n plus 1 stars means just one more star on n stars. So this is done by induction in set theory, not by mathematical induction. It's quite important that we really define this for all n from omega, from the set theoretical set of natural numbers, not just for metamathematical n. And then we define very important, in a certain sense, limit mapping of all the n stars, which we denote by dot. So the dot mapping of some set X is equal to the union of all the n stars of the set over all natural numbers n. And we will see on specific examples why union and how exactly this mapping behaves, but it can be considered as a limit of all the n stars. Notational thing very quickly, the mappings n star and dot have always the highest priority in our formulas. So when I write, for example, dot n and less than omega, and that it means that it's actually there are finite sequences from dot n. So the brackets are like this. Highest priority always for the stars and dot mappings. Okay, so this is how star gets iterated. And another thing from the title of this talk is iterating the star for the set of natural numbers. So we just need to look how star and then later the iterated star behaves on the set of natural numbers. And how the single star behaves is basically summarized in this picture, and I will fill in the details. That's the same picture here. And the first thing, very important one, is that the star mapping is actually identity on the set of natural numbers. So for any natural number n, star of n equals n. This is very easy to prove just by induction using the absoluteness of delta one definable operations. So the proof is written here. I will very quickly go through. So the first step of the induction is for the zeros. Star of zero is by definition the empty set. So star of empty set, and because empty set is delta one definable operations are star absolute, then this is exactly equal to empty set, which is again zero. And the same thing goes for the induction step, where star of n plus one, again by the set theoretic definition of what n plus one is, we see that only delta one definable operations are used. So we can use the star absoluteness for these operations and see that it's equal to n plus one. So star is identity on the set of n. But because the set n itself is infinite, that we already saw before, that star of the infinite set, so when we apply star on the whole set of natural numbers, then we get something which is larger than just the pointwise image. Because some non-standard elements, actually at least kappa of them, must be present. So there are some other numbers like this L, which are not in the image of star, but still are elements of the star of the whole set N. Okay, so another observations which are again denoted on the picture are that the set N itself, the original set of natural numbers, is of course a subset of star of n, because the mapping star is identity, so it gets mapped on itself. The second point is that the standard part of the star of n, of this extension, is actually exactly equal to the set n, to the original natural numbers. So the only standard elements in the extension star of n are the original numbers. And the remainder, this part which consists of non-standard elements, is of size at least kappa. I also already said that it follows from the saturation principle, because we can, if it wasn't at least kappa big, and we could create a centered system that would consist exactly of star n minus singleton of every element here, and star n minus singleton of every element also from the initial segment. And how many sets would we get in this centered system? It would be omega sets from here, and our assumption would be that it's less than kappa sets from the other part, so together still less than kappa. And any centered system of size less than kappa should have non-empty intersection, but of course this intersection is empty because we removed a singleton of every element of star of n. So sorry for talking the proof through, because it's inconvenient to write down on computer. So just if something is not clear, tell me and I will write it down on computer, but it's faster just to say it if it's simple enough. Okay, and the last set of properties which are related to this picture are the following, which concern the belonging of different sets which are depicted here to the different universes. So we already know that every natural number n from n is actually a standard element because it's equal to star of itself, and star of anything is standard by definition. It belongs to the standard universe. Although we know that any number L, which is in the remainder in this segment of the picture, is not standard, cannot be standard because only standard elements are the original natural numbers, but it has to be integral because the set star n is actually standard, therefore also internal. And the internal universe has the transitivity property. So element of the internal universe is also in the internal universe. So if L is in star of n, it must be also in the internal universe. And the second point of this proposition says that, of course, star of n, because it's star of something, then it's a standard element, standard set. But neither of the two parts, neither n, neither the star n minus n, are even internal. So both of these are external sets which do not belong even to the internal universe. And this can be seen in the easiest way by looking at the star n minus n, because this segment doesn't contain the least element. Of course, there is no least element here because the previous one would necessarily be in the largest element of n, which doesn't exist. So there is no least element here, which means that it cannot be internal set, because if it would be internal set, then it would violate the principle of mathematical induction, which is valid in star of n, which says that internally, any subset of star of n must have the smallest element. So if this would be an internal subset of star of n, it would need to have the smallest element. Okay, so this is just the basic picture. Try to keep it in mind for the later. And now another property which we will get again to some generalization of this property in a few minutes is when we take into account some structure on the set of natural numbers. So for example, the usual structure of arithmetics with 0 successor plus times and ordering. And we create the star image of this structure, and it's actually the structure which has everything, every component starred. And this star extension of the original structure is actually elementary extension of n, and it is kappa saturated for the given cardinal kappa. This can be seen quite easily. It basically follows from the transfer principle, but I will in a minute or two, I will prove even more general statement, and I will do the proof there. So I will postpone it from here. Okay, so the similar statement, of course, can be done for any language, not just this language of arithmetic, even for the full language of N, which contains a symbol for every function and every relation of any arity on N. Even for this language, we get the same thing, that we get the star of this structure is elementary extension of the original structure N. This isn't even limited to just N, it works for any structure. So taking the star of a structure actually is a universal way how to construct a kappa-saturated elementary extension. But that's not so important for today's talk. All right, so now we really start looking at the iterated extensions of the set N. So if you were lost in how fast I was till now, you can start listening again. You will maybe miss some reasoning in the proofs, but the most should be clear even if you didn't catch what I was just telling, because now we really start doing the main topic of today's talk. So we saw earlier that the set N is a proper subset of the star of N. And because this is a delta 1 formula, this relation is delta 1, then we can use the transfer principle and add stars to both sides arbitrarily. And by doing that, we actually get the following chain of relations, that N is a proper subset of star of N, that is proper subset of star star of N, and so on. And because the dot of N, we defined it to be actually the union of all the stars, star sets before, then it's also a superset, the extension of all the previous. So we have such extension. In fact, all of these extensions are end extensions. So the picture actually looks something like this. Do you see me drawing? I hope you do.
That I don't. I don't know if anybody else.
No, I don't see the drawing.
I'm not seeing it.
Mm-hmm.
It seems.
Yeah.
You probably have to end the share.
Yeah.
And then share the drawing screen.
And then reshare.
Oh yeah, so I give up. I don't know how to do that. So I will just continue here. You can probably imagine how this chain looks when drawn.
Right, but I have a quick question since we have a special interruption. So maybe you can explain, because I'm slightly confused. So these are end extensions with respect to the epsilon relation. So that's the same as the natural ordering on the numbers.
Yeah.
But then all these models are also kappa saturated. So all definable sets are supposed to be of kappa. So how does it? So if you take an initial segment, then it has cardinality. Oh no, I see. So starting from the first one, they already have cardinality kappa. So okay.
Yeah, starting from the first one. Yeah.
But so
exactly.
It's not grow. So the cardinalities are not growing. Once it's kappa all the way. All right.
Yeah, exactly. Okay. So this is the chain, and we will further on. We will denote the elements of this dot n of the limit of this chain, which is actually even the limit of the elementary chain, if you consider it in some language. We will denote them by Greek letters like alpha, beta, or nu, and the tuples of such elements will be denoted with a bar. So whenever we have some element alpha in dot n, then we define the rank of that element as the minimal n such that alpha is in n stars of n. So the minimal stage in this chain where the alpha first appears. That's the rank of alpha. So elements of n have all rank 0. Elements which are in star of n but not in n have rank 1. These elements which are not before have rank 2, and so on. Rank of every element is a natural number. So every rank is finite because dot n is actually union of everything before. So every element of dot n already appears in some of the previous sets. And the rank of the tuple is the maximum of the ranks of the individual elements. So again, basically, it's the first stage where the whole tuple appears in the hierarchy. So that's the rank of element and tuple. If you wished, you could define this even more generally, not just for elements and tuples, but also for any hereditarily finite set. So you could define the rank also on the dot of V omega in the same, completely the same way, because for the V omega, star of V omega, and so on, the dot of V omega, you get the same chain as for the n, but we will not need it here. I'm just saying that if you wanted to have something for some rank, for example, for something other, some other finite structure than just a tuple. Okay, and now we get some generalizations of all the principles, of the basic principles which I mentioned before. The most important of them, again, is the transfer principle for dot of n, which again talks about delta 1 formulas and says that whenever we have some tuple alphas in dot of n, then we can arbitrarily add or remove stars in parameters in the formula phi and stay equivalent as long as the number of stars on both sides is at least the rank of alpha. So this is quite important, that we cannot take less stars than is the rank of alpha, than the stage where the alpha appears. But whenever we have more or at least the same number of stars as the rank of alpha, we can choose it arbitrarily and stay equivalent for delta 1 formulas. The proof is quite easy using the original transfer principle, but I will probably skip it so that I can get to the really interesting parts. So it's written here. Maybe you already went through with your eyes. Very, very easy, but I will not talk about it. And corollary of this transfer principle is the following relation between the structures. So not just the sets, but we now have the full structure of all functions and relations on n. So the set S contains symbols for all the functions and all the relations of all arities on n. And in this language, the structure n is elementarily extended by adding stars repeatedly, and of course the structure dot n is the limit of this elementary chain, so it's the elementary extension of all the previous. This is immediate consequence of the transfer principle, because the key thing that we need to prove is that whenever in some n star n some formula psi is true about some alphas, which are elements of the n star n, then this is true anywhere above in the hierarchy. And we get that immediately from the transfer principle, because this truth formula, this truth relation is actually delta 1 epsilon formula, to which we can apply the transfer principle and move it at more stars.
So apologies, can I ask a quick question now?
Mm-hmm.
So with this corollary, is this actually all that you will need for the rest of the talk?
Probably yes. In this sense, yes.
So in a sense, you could have started the talk by saying, well, let's have this chain of elementary extensions, and they're all kappa saturated, and then just move on.
Yeah. Okay, yeah. So now I understood your question. No. I will probably use the transfer principle itself and other properties besides that. I couldn't start with just this.
All right.
Yeah. Okay. So now the first, now we get really to the study of the structure of the dot n. So the first thing which I would like to talk about is indiscernible sequences inside of dot n. So at this seminar, Models of PA, obviously everybody knows what indiscernibles are, so it's just written here what indiscernible sequence means. So indiscernible, some infinite sequence of betas is indiscernible whenever with respect to some formula phi, whenever the formula holds equivalently for any two increasing subtuples of the sequence. And strongly indiscernible, although I think, which is a very known concept, is just a strengthening of this property, which says that actually the equivalence holds true also with some parameters, provided that the parameters are at most equal to some element beta k, which precedes all the elements of the sequence which appear in the formula. So that's strong indiscernibility, although I think everybody knows this concept. And now let's look how indiscernibility looks like, or how indiscernibility appears inside of dot n. And actually, I will prove here as the proposition that the sequence which is created by starting from any element beta from dot n and then taking in each step, adding a rank of beta many stars to the beta. So we are going in steps of length rank of beta. So if beta is of rank 1, then it's just beta, star beta, 2 stars beta, and so on. If beta has a rank higher, then we are going in multiples of the rank of beta. So this is the sequence, and this sequence actually is strongly indiscernible, and even more than that. Exactly what holds is written in the proposition for any, not only bounded here, even delta 1 formula is possible. So even for delta 1 formulas, the following equivalence is true. So we have the betas, any two increasing subsequences of the original sequence of the betas. And then we have two types of parameters, parameters alpha and parameters y. Parameters alpha are, as the Greek letter suggests, taken from the dot n. So there are some numbers in dot n, and parameters y are any sets. So they can be outside of dot n. And whenever the two subsequences are increasing and the alphas are such that the rank of them is actually at most the lowest number of stars applied on both sides, and the number of stars applied to the parameters y is higher than the highest number of stars applied, actually one more step of rank beta higher. These are these two inequalities. Then the two formulas are equivalent. So the proof is technical, but it's only application of the transfer principle. Sorry?
A question. Can you say again about y bars? Where are the y bars from? From anywhere?
Anywhere. Yeah. There are so any sets.
Anywhere in V?
Anywhere in V, yeah. anywhere in V, any sets, arbitrary sets. Okay, so this is the proposition, and actually the corollary, or the more easily sayable property which is contained there is so-called rank indiscernibility, which is even stronger than the strong indiscernibility, but it's specific to the .n setting where we have the rank. So sequence is called rank indiscernible whenever it is indiscernible with parameters that whose rank is at most the rank of some beta k, where k precedes all the indices of both the sequences. So the z's, the parameter z's, don't have to be smaller than beta k, they can be even larger. It's sufficient that the rank is at most the same. So it's stronger than strong indiscernibility by allowing even larger parameters with the same rank. And this property follows from the previous proposition. So we have the corollary, which says that this sequence of the start betas is actually rank indiscernible, and therefore also strong indiscernible and indiscernible with respect to all parameter-free delta 1 formulas, and also with respect to all parameter-free formulas of the structure .n, because all of these can be rewritten as delta 1 formulas. All right, so this is indiscernibility. Why is it important for us? Is the following. As you know from arithmetics elsewhere, indiscernibility is always somehow connected with Ramsey properties. So the most immediate connection here is the following. Actually, the previous result already gives us a version of Ramsey's theorem on .n, which is not that interesting per se, but it will be interesting in comparison with the real Ramsey theorem on n, which we will more or less derive from this using a more complicated machinery. So this proposition says that if we have any finite coloring of increasing n tuples of natural numbers, this notation, increasing n tuples, then there is one color and some infinite subset of .n, such that this infinite set is actually homogeneous with respect to that color, in this sense that the increasing n tuples from the set A all have the dot extension of the color, because we are now living in the dot of n, so also the color which was originally on n is extended to the color of dot of n, elements of dot of n.
And I understand infinite means unbounded.
Yeah, sorry. Yeah, infinite means also unbounded, yes. I could have written cofinal here. Yeah, it would be maybe clearer. It's cofinal in .n, unbounded. Yeah. Okay, and the proof is very, very easy. The infinite set can actually be taken canonically always the same as the set given by the sequence, by the indiscernible sequence of the betas, as we saw it before. And of course, then any increasing subtuple of this, or we take the first one, we take just the first n elements, and they have some color. They must have some color because every n tuple has some color, and this color will be the color which exists according to the theorem, and that all other increasing subsequences or all other increasing subtuples, n tuples of A have the same color is given by the indiscernibility with respect to the formula x equals n dot c, which is delta 1. So this is an immediate consequence of the indiscernibility of this sequence. What would be nice would be if we could now, because we know that .n is elementary extension of n. And it would be nice if we could just take what we have proven, the Ramsey theorem, on the set .n and transfer it down to n, so that we would actually get a proof of Ramsey theorem on natural numbers in the classical setting. But this isn't possible to do naively, because of course the statement of the Ramsey theorem contains existence of some infinite set, and this is not a .n formula. This is not formula in the language in which the elementary extension is. So this cannot be done directly, but it will be possible to somehow collapse this property from .n down to n, but we will need to study the structure of .n a little bit more. So the first thing which we will need to know is actually something about not indiscernibility, but indistinguishability. And indistinguishability in this sense is just an equivalence relation on .n. Two elements, alpha and beta, are said to be indistinguishable by standard properties if for any subset of n, just n, they are, one of them is the dot extension of the set, if and only if the other is. So they are not distinguishable by the subsets of n. So that's the indistinguishability relation tilde. And this relation, of course, is non-trivial. It's not identity. For example, every alpha is indistinguishable from any number of stars applied to itself by, for example, the elementary property, by elementarity in the .n, because A is sum of the relations in the language. And in fact, if you look at this topologically, then this equivalence exactly corresponds to the checkstone compactification beta n of n. So basically, the right side of the definition defines some ultrafilter, and this is the correspondence with the checkstone compactification. And it would be nice now if this was not just equivalence, but if it would be also a congruence with respect to at least some functions like addition or multiplication and some basic relations perhaps. So here it is just recalling what a congruence means. With respect to function, it's clear, everybody knows that. With respect to relation, it's not so used. So
sorry, but I have one question about this checkstone compactification characterization of this indistinguishability. So you define it, you define the ultrafilter in terms of .a. What happens if you stop sooner? If you define this same relation but with star A or n star A, do you get some kind of a approximation? Do you get some kind of something on the way to compactification or something coarser?
You get exactly the same thing. Actually, you cannot, you don't define the same tilde relation, because if you are using only n stars of A instead of the dot, then you can define the tilde at most on n stars of n, because you cannot go higher with that.
Oh, I see. But
so different tilde, but the same same topology.
Okay, thank you.
Yeah. Okay, so the congruence for relations, what does it mean? For equivalence to be congruent with respect to some relation P, it means exactly the thing that whenever two tuples are equivalent, then the relation holds equivalently about both of them, granted that, granted that that's for the function. partial functions, we require that at least one of those functions actually makes sense or is defined on the tuple. Okay, so this is what congruence means, is the usual thing, so I will not take more time there. And it would be nice if the indistinguishability relation, the tilde, actually was a congruence with respect to at least some functions. Sadly, this is not the case. It's not a congruence with respect to addition or multiplication, or actually it's not congruence with respect to most functions of arity larger than 1. Here is a very short example which proves that it's not congruence with respect to addition. So what we do in order to prove this is we take some element nu in .n such that the binary valuation, so the highest mu such that 2 to the power of mu divides mu, is we take some element like that such that this valuation is non-standard. It's larger than any standard number. So we take alpha non-standard such that the binary valuation, which we denote beta, is non-standard. And then we of course have that alpha is indistinguishable from star of alpha. It's true about all elements, that they are indistinguishable from their stars by the transfer principle, for example. But alpha plus alpha is not indistinguishable from alpha plus star alpha. So both of the arguments on left and right are mutually equivalent, but the results of the operation are not, which means it's not a congruence. We need to prove just that this non-equivalence holds, that alpha plus alpha is not equivalent to alpha plus star alpha. And we do that by computing the valuation of both sides, the binary valuation of both sides. So the binary valuations first, just of the star of alpha, is star of beta, because valuation of alpha is beta. By transfer principle, this valuation is delta 1 definable. So by transfer principle, we can add stars to both sides and we get the valid equality. So valuation of star of alpha is star of beta, and because beta was non-standard, then star of beta is larger than beta. It's in the higher stage of the hierarchy on .n, so it must be larger. And therefore, when we compute the valuation of the sum, alpha plus star of alpha, then it's actually equal to beta, because valuation of alpha is beta and valuation of star of alpha is larger than beta, which means that the valuation of the sum is the lower of the two, which is beta. And the other side of the non-equality, non-equivalence, the valuation of alpha plus alpha is the valuation of 2 alpha. And because valuation of alpha is beta, then the valuation of 2 alpha is beta plus 1. So we see that the valuations are different, and actually not only different, but also of different parity. One of them is odd, the other is even, because they differ by 1. And therefore, when we take a set A, which consists of all the numbers whose valuation is odd, then this set actually distinguishes alpha plus alpha from alpha plus star alpha. And therefore, they are not equivalent in the indistinguishability equivalence. So to repeat what we just proved, we proved that the tilde, the indistinguishability equivalence, is not congruence with respect to addition. So that's bad enough, but luckily the indistinguishability equivalence is a congruence with respect to a large class of functions, and they are so-called graded functions and relations, which I define just on the next slide. So what grading is? Grading is actually a transformation of the finite tuples of elements from .n onto some other finite tuples of elements from .n, which works in this way. Some finite tuple graded, denoted by the up arrow, is just the same tuple, but we apply more and more stars to each element of the tuple. So we start with the first element of the original tuple by alpha 0, unchanged, but to alpha 1, we apply as many stars as is the rank of the previous element, in this case alpha 0. So rank alpha 0 stars applies to alpha 1. Another element again is created from alpha 2, from the element of the original tuple, by applying as many stars as is the rank of the previous thing. And the rank of this thing is actually rank of alpha 0 plus rank of alpha 1. Can be easily seen. And so on until the last element, which is the last element of the original tuple, where the number of stars which we apply is actually the sum of the ranks of all the previous elements alpha 0 till alpha length minus 2. So this is grading. It somehow gradually adds more and more stars through the tuple. And we also can grade functions and relations. So the function graded applied to some tuple is nothing else than just the dot extension of the function applied to the graded tuple. And the same for the relation. Graded relation on a tuple is just the dot extension of the relation applied to the graded tuple. So very, very important special case of this is for addition and for multiplication, where you can see how this works on a specific example. Graded addition, alpha graded plus beta, is just alpha plus and as many stars on beta as is the rank of alpha. So rank alpha stars beta. And the same for multiplication again. Multiplied by the rank alpha stars of beta. All right, so those are graded operations and graded relations. And the most important connection to the indistinguishability relation is that now we can actually prove that the indistinguishability equivalence is a congruence with respect to all graded functions and all graded relations. So not to the original plus, but with respect to the graded plus, it is a congruence. And this is very important, which can be applied in the Ramsey combinatorics. The proof is technical again, so I'm skipping it, but it's not that hard. It's just using the delta 1 comprehension and its star absoluteness. And very special important case is for unary functions, because unary function takes as argument just one tuple, and one tuple graded doesn't change because the first element of each tuple doesn't change when graded. As we saw here, the first element doesn't change. So for unary functions, the graded function is actually equal to the dot extension. And therefore, for unary functions, we get that the indistinguishability is actually congruent with respect to the original dot extension. We don't need to grade unary functions. But for arity higher than 1, we need to grade them in order to get congruence. And the last structural thing that we need to know about dot of n is the topology, which is on dot of n. And the topology can be defined by or in two different ways, which are equivalent. One is the classical way, using classical topology, meaning not non-standard topology. That's on this slide. So how do we get topology in game is first taking the factor structure of dot n, by the indistinguishability relation. We can not only factor the set, creating n tilde, but we can also take factors of all the functions and all the relations, because the indistinguishability relation is congruent with respect to all of them, as we just saw. So we can factor all functions and the relations as well. And in such a way, we get the factor structure. And on this factor structure, tilde n, we actually get the canonical topology, whose basis of this topology is given by the upsilon of by the sets upsilon of A for any A subset of n, where the upsilon A consists of all the equivalence classes of elements that are in the dot of A. This is basically, again, the checkstone topology. Nothing else, or not that different. So this topology actually turns out to be uniform. It's not that important how exactly the basis of uniformity looks. It's written here, but I will not read it. And not only uniform, but also compact and Hausdorff. And this is important, that it's compact and Hausdorff. So that's the statement about this topological space. It's a uniform, compact Hausdorff space. And another important thing is that all the factor functions given by the, or created from the graded versions of the original functions are continuous in the first coordinate with respect to this topology. So not continuous in all of the coordinates, just in the first one, but it will be enough for everything we need. Okay, again, the proof of this isn't that hard, but I don't have time to do it here. Instead, I will give a quick note of the alternative definition of the same topological space, which can be done completely in the non-standard way, which is maybe more enlightening if you know some non-standard topology. So the same space as, sorry?
But I have a technical question.
Yeah.
How much more time do you need?
Oh, sorry, I am 5 minutes over time. 5 more minutes.
Okay.
Is it okay? Yeah.
No, it's certainly fine with me. It's just good to know, because I see that some people have left already. Usually we go over about an hour, but and there are other things. Anyway, I just 5 minutes is certainly fine.
Yeah. Okay. Okay. I try to manage in 5 minutes. Okay. So this topology of indistinguishability actually can be defined also in a non-standard way, where we actually define something called indifference phase, which is non-standard version of topological space, not just on dot n, but on star of dot n. So even one more star beyond dot n, that's the highest number of stars that are used in my talk. And again, I will not go into details here. The basic indifference relation we get is the relation double tilde, which is defined basically in the same way as the tilde before, the indistinguishability by standard relations, but now with the one more star applied everywhere, because we are one star higher. And if we just take this topological space given by this equivalence, we wouldn't get Hausdorff space. It would be non-Hausdorff. Therefore, we need to create Hausdorffization of this space. So the courses space, courses factor space, which is already Hausdorff. And this is created by taking this original space with the double tilde and factor it by the star of the original tilde relation. So we can apply star even on this equivalence of indistinguishability and factor this structure by this, and what we get is exactly the same topology as on the previous slide, just done in the non-standard way, with the same properties being compact Hausdorff and having the continuous functions in the first coordinate. And why I was doing this is actually to talk about the last thing from the structure of .n, which are idempotent elements. Any element alpha of .n is called idempotent with respect to some function g if actually the factor class alpha tilde is idempotent element in the structure, in the factor structure tilde n with the tilde g, in the sense that g, tilde g applied to all the tilde alpha on all the places is equal again to tilde alpha idempotency, classical idempotency. This can be rewritten using all the definitions that alpha is actually g idempotent if and only if the graded g applied to all alphas is indistinguishable from alpha, from the original. And again, the special cases for addition and multiplication are written here. Alpha is additively or multiplicatively idempotent if alpha graded plus alpha actually is indistinguishable from alpha, and the same for the multiplication. So these are idempotent elements. And because I don't have much time, then I just quickly say that there are some results from the theory of topological semigroups, like Ellis-Numakura lemma, which states that under certain conditions, if S is a semigroup with compact Hausdorff topology, then the idempotent elements actually exist. And because we just proved that we have a compact Hausdorff topology on our vector space, and we can use this to prove the following proposition, which says that actually for any associative operation on some subset of n, there is always a G idempotent element alpha in the dot extension, actually even in the first star of X. Okay, and last minute or two, which this applies, of course, to addition and multiplication as special cases. And the last thing I would like to only show you, I will not do the proof, sadly, no time for that, is how this can be applied to prove some of the hard combinatorial theorems. For example, the Hindman theorem, which is the following statement, which says that for any finite coloring of natural numbers, there is an infinite set and some color, such that the set is homogeneous in the following sense. In the sense that any finite sum of elements from A has the same color C. So we get infinite set such that any finite sum from this set has the same color. That's the statement of the Hindman theorem. And all the machinery I explained before can actually be used to prove in a very fast way. The proof is, I hope you will see it, how long it is only. So sorry for this. Proof is just few lines, basically. This is it. So this is the proof, few paragraphs. That's the direct proof that uses every theory I just went through. So it's in the lecture notes that I sent you the link. So you can go through it by yourself, hopefully, through the direct proof of Hindman theorem. And it's even possible to prove some general statement, very, very abstract one, which allows the Hindman theorem to be proven even by the proof which is just 4 lines. 4 lines long, which is extremely short proof, and it's the same abstract principle can be used also for the proofs of all other Ramsey type theorems that I know of. Even the Millikan-Taylor theorem can be proven by this. Unfortunately, I don't have time to go through all these proofs. They are a bit technical, a lot of computations in there, but very short. So that's where I end now. Thank you for your attention. Here's the link for the lecture notes if you didn't get it before. You can find all the details there, and thank you again.